We do not know where the universe came from. We do not have the complete user's manual for the universe. We have parts missing. And the birth of the universe could be on those hidden pages.
Astrophysicists confirm that 95% of the universe is missing.
95% of the stuff in the universe, so 70% is dark energy. What is dark energy? We don't know.
Geraint is one of the world's leading astrophysicists, a professor at the University of Sydney, speaker at the Royal Institution, and the author of Where Did the Universe Come From?
How do we look at the beginning of the universe?
So this is an area where Stephen Hawking sort of thought about the universe, that the universe crystallizes out of a true nothing. Well, it looks like in our universe we have a very well-defined set of numbers that allows the universe to have complexity. And from that complexity, we get the ability for the universe to host us.
Geraint, it's an absolute pleasure talking to you. Thank you for joining me. You're an astrophysicist,
yes,
cosmologist, someone who's dedicated their life to understanding the universe, stars, galaxies, mysteries of the universe. What's that one mystery that you think most about, or sort of at night you wonder about, which sort of haunts you the most?
Oh, I wish I could say there was one mystery about the universe, but there's a whole host of them that sort of occupy my mind. So there's one really focused on my research, and a lot of my research is on the dark side of the universe, the stuff that we know that's out there but we can't see and we haven't yet gotten hold of in the lab, and just to know what that is, because it's the dominant stuff in the universe. But there are bigger questions that I also wonder about, such as, where did the universe come from? What was before our universe? Was there anything before our universe? Mm-hmm. Is our universe alone? Are there other universes, etc.? So, yeah, there's more than one mystery, but that's part of the reason why I've been in this game for more decades than I care to remember, mm-hmm. is that there are always mysteries. Some of them we solve, others might have to wait until after my lifetime.
Mm-hmm. And so one of the things that we wonder quite often is that universe,
mm-hmm.
where does it come from? So you've written one of these books. Where
Yes.
did the universe come from?
Well, the answer would be that we do not know. And it's an interesting question of why we don't know. I think that is the important question. So one of the great successes over the last century has been this study of cosmology, understanding the universe. And it's in that 100 years, we've learned that we live in an expanding universe. We live in a universe that had a start. It had a birth in the Big Bang. And we can actually work out how the universe has operated over these billions of years, from the initial fractions of a second to the 14 billion years old that the universe is today. But our understanding of the laws of physics doesn't let us look further back. So we sort of look back and back and back and back, and to a point, as I said, such a tiny fraction of a second after our current universe came into being. But we haven't yet cracked the physics and the maths to look further. So we do not know where the universe came from. We have ideas, we have hypotheses, but it's been a mystery that we haven't been able to solve now for, again, 100 years. As soon as people realized that our universe had a beginning, people started asking, well, what was before? And there were claims that, of course, the person that came up with this concept of the birth of the universe was Georges Lemaitre, a Belgian. He was actually a Catholic cleric, and he was accused of trying to smuggle creation back into physics, right? That you needed a god to kick off the universe. But in terms of a scientific question, there are a whole bunch of alternatives. There's the most simple possibility is that our universe was born from nothing. A true nothing. Mm-hmm. And like, if you ever want to get into a fight with a room full of philosophers, get them to define nothing, right? We are not talking about empty space, right? Which is what you normally think of when it's a nothing, but it's a nothing that has no space and has no time. So this is an area where Stephen Hawking sort of thought about the universe, that the universe crystallizes out of a true nothing. But there are many others that think that our universe is part of an endless cycle, that, the universe is born, it lives, and it dies. And there's a I wouldn't say mainstream idea, but there's a thing called the epkairotic theory. I think it's Greek for born in fire, which means our universe has a big bang, it ages, it gets very, very old, and then it sort of undergoes a rebirth by colliding with another universe, right? But then there's this entire notion of what's known as the multiverse theory, that universes are being created. We don't quite understand the process. We have some ideas that related to this immense rapid inflation that we had in the early universe, and that our universe is effectively one universe that was created via some process, but in a sea of maybe an infinite number of other universes, right? So yeah, we have lots of ideas, and people are proposing tests for these ideas, but we're confined to one universe, and it's very hard for us to imagine what test we could do that would conclusively reveal that we're part of a multiverse, or that we came from a previous universe to today. But we're still looking.
But is that knowable, you think? Do you think that for something that we assume that started out of nothing, which is, so it is non-physical, whatever that nothing is?
No, I wouldn't put it in the realm of non-physical. You have to be careful with terminology in when we're talking about the sciences, right? So we can have physics, and then we can talk about metaphysics, and then you can get into the spiritual. And I can tell you that I definitely cannot prove that there's not an invisible unicorn standing right behind you, right? I can't do that. Yeah. But I think the question of the birth of the universe is something that we have the potential to grasp. We know for certain that our laws of physics as we understand them are not complete. We do not have the complete picture of the universe. We do not have the complete user's manual for the universe. We have parts missing. And the birth of the universe could be on those hidden pages. And this is a bigger question, which are these grand unified theories, and then theories of everything, where we really can encapsulate and capture all of the physical laws in essentially one framework. And people think that if we get to that point, that barrier that we've got in our current physics that stops us seeing the birth of the universe, that will be opened, right? And we will be able to see through. And we will know then where our universe came from. And if the mathematics at the end of the day says, yes, Hawking was right and it came from a true nothing, then we'll be fine with that, I think. But I think it would be more exciting to find out if we're part of something bigger, right? Yeah. I mean, we like to think, of course, like our universe, which is potentially infinitely large in terms of its spatial extent, that there is more to what we have around us. Mm-hmm. So yeah, I think it's potentially within grasp, but as always, when you're trying to predict the future, in the future of physics, I can't tell you what breakthroughs there are going to be, right? It's very hard to do that. Mm-hmm. But it's imaginable that it will become within our grasp.
Right. The universe, as you said, started from nothing or a point of infinite density or size, right? And then there was a big bang, right? And then there are these constants that exist, yes, in our universe, so to say. Right? Could you talk a bit about those constants and how they play a role in our sort of universe in formation and then the way it exists at the moment?
Yes. So one of the things that is kind of when you become a physicist, you sort of do this stuff and you get the mathematics and it all sort of makes sense, but at some point something hits you, right? Is that physics has to be more than the mathematics. And what I mean by that is that I can write out the equations for, say, the law of gravity, right? So how do two masses attract each other? This is something that Newton worked out. He worked out the mathematical relationship for how this mass attracts that mass. But he had a mathematical relationship, and it was made of the masses of the objects and the distance apart. But there was another number in there, which we called the Newtonian gravitational constant, okay? Big G. And without that number, you don't know how big the force between two masses is. So the question is, right, where do I get that number from? Is it a number like pi, right? You know, it's got a mathematical definition. No. For G, to work out how gravity works and use those equations, I have to go out and measure G. And there was a famous experiment done by Cavendish way back in 1700s, late 1700s, 1800s, measuring the value of G. So up until that point where you've measured that value, those equations are sterile. And it turns out that in all of physics, there are numbers that we have to ask nature for. So Einstein's relativity, we can't use that until we know what the speed of light is. So how do we know the speed of light? You have to go and measure it. Right? You may say, oh, but you can actually mess around with electricity and magnetism, but they've got their own constants in there, which you have to go and measure. So throughout physics, all of physics, there are fundamental constants, and they have values. And so in our universe, the speed of light is 300,000 kilometers per second. The gravitational constant, a number like 6.67 times 10 to the minus 11. These numbers get imprinted in your mind.
Yeah.
And you have to ask yourself, well, why are they those particular values? Now, at one level, that question is trivial, right? Because the speed of light is a number that has dimensions. We measure it in meters per second, or kilometers per second, or miles per year, or whatever number you want to do in, right? So it has a numerical value tied to our system of units. But we have constants and combinations of constants that have no units. And the most famous one of these that many people know about is something called the fine structure constant. So it's normally written as 1 over alpha, the Greek symbol alpha, and it has no dimensions. So it's not meters per second or anything, it has no dimensions. So all of the dimensions have cancelled out in the way we use this number. So we have to go and measure it in nature. And of course, because it has no units, it doesn't matter what your measuring equipment is. At the end of the day, you'll get the same number. And it's a number like 1 over 137.15 or something. It's some number.
Okay.
Why that value? Why that value? Why 1 over 137? Well, why is this important? Well, it's because the fine structure constant tells you how strong the electromagnetic force is. And so if it was 1 over 30 or 1 over 30,000, we would have different electromagnetism. Now, you might say, oh, okay, but if we've got different electromagnetism, then doesn't everything sort of just work out? And we can explore that. We can explore hypothetical universes, right, where we try different values of these constants, okay? And again, not worrying about the units aspect. We do ratios such that it's dimensionless. And we find something kind of bizarre. We find that in our universe, if you look at the mix of numbers that we have, the constants, that in our universe, those numbers, right, they control what's going on with electrons and positrons and atoms, etc., right? But because we are made of atoms which are bound into molecules, which are bound into cells, which are bound into acids, etc., you start mucking around at the bottom, and that influences what happens at the top. And it turns out that if you start to adjust these numbers and ask, well, how would the universe have been different if electromagnetism was weaker or gravity was stronger? It's very easy to destroy a universe. And what I mean by that is that you can rob a universe of complexity, right? Now, complexity it might sound like a weird thing to talk about, but when you look at us, right, we are a molecular machine, and we are built of complexity, and it's very difficult to define life, but one of the key things about life is it appears to be information processing, energy processing. You need complexity, right? If you have universes without complexity, then you have no prospect for life, right? So what are we saying about that? Well, it looks like in our universe we have a very well-defined set of numbers that allows the universe to have complexity, and from that complexity we get the ability for the universe to host us, right?
Oh,
Right.
so it's more about complexity.
It's more about complexity. So unfortunately, this is tied to something called the anthropic principle. And of course, the anthropic makes it think, oh, it's about me, or it's about humans. But it's not. It's about complexity, right? So this is the real sort of key point, right? Because if you imagine I made a universe and I made gravity very strong, then in that universe, then very quickly matter would gather together and collapse into black holes. Now think about it. What would the possibility of life be in a universe that contained only black holes? Now, it's very difficult. What do you build any life out of? Right? You can't have. It's very difficult to do information processing, etc. Imagine that we have a universe where instead of there being a mix of protons and neutrons at the start of the universe, there's only neutrons. Right? Those neutrons could be stable, right? You can make them stable, but they can't join together to form molecules.
Right. So there isn't the right mix to. Yeah.
Yeah.
Okay.
You could. It's very easy to make a universe with a periodic table with one thing in it. Right? And you can make a universe where protons and neutrons don't stick together. That's very easy to do because they only just stick together as it is to form deuterium. So if you have a universe with just protons in it, your periodic table has one element, hydrogen, and it has one chemical reaction, which is forming molecular hydrogen. That's it. Right? So you run out of possibilities for life. So this is what's known as the cosmological fine-tuning problem. I wrote a book on that too. That's what this book is done here, right? A Fortunate Universe. In that, it's very easy to, by adjusting these fundamental constants, to come up with dead and sterile universes. And the question is then, why do we live in a universe that has the possibility of this complexity? And of course, the first answer is trivial, because we couldn't find ourselves in a universe that doesn't allow us to be here. Right. But then you have to say, well, okay, but why does our universe have these particular sets of numbers? And we don't really know. Right? For some people, and a large number of people, there's a theological solution, that it was fine-tuned by a being that wanted us to be here, right? But from a scientific perspective, it's a tough question answer. So some people would say to you, oh, well, maybe these numbers, right, the fine structure constant, maybe it really is a mathematical relationship. Maybe if we just thought a lot harder and did physics a lot better, we would find that the fine structure constant is 1 over pi to the 5th times e to the I something or whatever. You know, you come up with a purely mathematical number for all of the constants. You'd find that you get to the bottom of physics, there's no freedom left. You don't have to ask nature for anything. You've got it all. But then you're still left with a problem. Okay? You're left with the problem of, why does our universe use these mathematics, right? Because one of the interesting things about maths, of course, is that the library of possible mathematics is infinite, and the universe only uses a subset of that mathematics. Why is this subset and not that subset? Right? So even if we got to the bottom of all the maths in the universe, we have to ask why the maths that we've got. Then you run into things like, well, maybe what we're dealing with is a simulated universe, right? So I hate to say this, but this is something Elon Musk likes. But this notion that, you know, the reason that we have the conditions that we do is that this is a computer simulation by some being in a higher dimension, a higher space, or whatever you want to call it. And the reason that they're running a simulation of this universe with these numbers is that it has interesting outcomes. They've tried other numbers, you get boring outcomes, so you try in these numbers. And of course, the simulation hypothesis has lots of problems, and that's why it's a hypothesis. No matter how much the philosophers dine out on it, it's a very difficult thing to kind of solve, which is why I prefer the multiverse solution, right?
Yeah.
That universes are being created, whatever the mechanism is, but there's something stochastic going on, something random in the way that universes form, such that you're basically granted a set of fundamental constants as a universe is born. And ours was born with this number, and we shouldn't be surprised to find ourselves in a universe like this because it allows us to be here. But other universes that got the wrong mix or a different mix of constants are dead and sterile.
Right.
Which means that, if you want to think about the sea of potential universes, that the vast majority of them are dead universes. Every so often there will be an island where a mix of numbers, right? Ours is not the only mix. Universes close to us will be possibly similar. There might be islands of other mixes of numbers that give you possibility for complexity, but the vast majority of universes are going to be dead. And so, it just seems so uneconomical, doesn't it, to have this multiverse full of dead universes, just such that we've got us here, something else over there, etc. But to me, it seems like really the only reasonable kind of solution that you have for fine-tuning, other than basically shrugging your shoulders and saying, well, that's just the way the universe is. Yeah. Which to me is not a very satisfying thing.
Yeah. I mean, could it be that it's a combination of both, some sort of a simulation where the game is that there are these universes being born and dying with time, but they're not, and their aim is to achieve different levels of complexity.
It could be. I mean, this is partly one of the issues that you run into in thinking about this, is that you run into the science fiction solution very quickly. And of course, the simulation hypothesis effectively is a science fiction kind of solution. You can dream up many possible solutions. I think the problem that we have is that in terms of the scientific possibilities, it's very hard to tell. I mean, impossible to tell that we're in a simulation. So put it this way, right? I mean, if you imagine that we are a simulation, what might you imagine that we're made of, right? So if you think of our kinds of simulations, my students simulate universes, right? They're relatively low resolution. We don't think they've got consciousness in them. But, they're made of particles, they're made of pixels and all that kind of stuff. And you might think, oh, well, what if our universe on some scale is pixelated, right? What if we look down there on that scale and see pixelation? Does that mean we're in a simulation? And some people would say, well, no, because already like loop quantum gravity says that the universe on some tiny scale is pixelated. So you end up looking around and everything you find in nature, you sort of say, oh, well, that's just part of physics. It's just part of nature, even if it's pixelated. Maybe the only way we'd find out if we're in a simulation is if a giant game over sign appears in the cosmos, right? But it's a very difficult thing to do if we are just running in a simulation. Anything we find, we would encompass in our laws of physics.
Right. Let's go sort of early to the beginning. Right? So let's say if there was this cycle of birth and death of universes, let's go in the how do we look at the beginning of the universe? So being a cosmologist, or what tools do you use, or the field uses to look at this is how the universe started, and before. Okay, we'll talk about before a little later. How do we investigate that this is how the universe started?
Okay, So as I mentioned, what we have done is we've pushed back, right? So if you can imagine through our telescopes, when we look out into space, because the speed of light is finite, the further we look back, the further back in time we are seeing. Right? So the sun that we see in the sky right now, that light left the surface of the sun 8 minutes ago. So I see the sun as it was 8 minutes ago. The Andromeda galaxy, which is the nearest large galaxy to our own, I can go and look at that with the telescope, but the light that I'm receiving set out from Andromeda 2 million years ago. And the further we look out, the further we look back. So you might just say, oh, we'll just keep looking further and further, and because the universe is only 14 billion years old, surely, if we look back over 14 billion years, we see the birth of the universe. Mm-hmm. And the problem is that the universe, up until around 400,000 years old, was opaque. It was a plasma, so it was made of the nuclei of atoms. It was mainly protons and electrons that hadn't bound together. The universe was still hot, so they were bouncing off each other. And the presence of these electrons means that light can't propagate freely, right? So the universe was opaque. So when we look out into the universe, the furthest we can look back is to a time which was 380,000 years after the Big Bang. So the radiation we receive at that point when the universe became transparent, that is known as the cosmic microwave background radiation.
Right.
Okay? Mm-hmm. So we see that in all directions. It was discovered in the mid-1960s. And effectively, that radiation that we see is the leftover fireball, right? So today, that radiation is really cold. It's about 2.7 Kelvin, so 2.7 degrees above absolute zero. Back 400,000 years after the Big Bang, it was about 4,000 degrees. Okay, and we can use our laws of physics to go back further, right? We know the universe is expanding, so as you go back, it must have been smaller. And we know that if you take a gas and you squeeze it, it gets hotter and hotter and hotter. So we can work out the temperatures of the universe as we go back. Okay, so we can go back after 380,000 years, back. We just know that the further we go back, the universe is hotter and hotter and hotter. But we get to a stage where, we know how plasmas behave, but we get to a stage when the physics that was going on was nuclear physics. Right? And we know how nuclear physics works. There was an epoch in the 1940s where people were very interested in nuclear physics, right? Especially in the building of hydrogen bombs. How do things stick together? So we know that nuclear physics operated at a time, the first couple of minutes after the Big Bang, right? Yeah. That was the formation of the first elements. We push back even further, things get even hotter, right? So when you have a temperature scale, which is nuclear physics, you push back even further. Not even nuclei can exist anymore, right? So you push back into the realm of particle physics. So again, we've got our laws of physics, and we're just winding it back and asking what were the conditions of the universe like as we go further and further back. The success that we have, though, is that those events that occurred early on in the universe, even though we can't see them directly, leave an imprint on the universe around us today. So in the first 3 minutes where we had that nuclear physics operate in, we formed the first nuclear elements. And the problem that we had is that the universe sort of cooled off too quickly. So in the first few minutes, the universe created, of course, it had protons, so it created hydrogen, and it made helium, and it made a little bit of lithium, and then the nuclear physics ran out of steam. The universe cooled down too quickly. And there's a prediction that comes out of those first 3 minutes that said that the baby universe was 75% hydrogen, 25% helium, and then trace elements for everything else. And you might think, oh, well, okay, that's what the universe was like at the start, but what about today, 14 billion years later? Stars have created heavier and heavier elements, right? But they only do that in the cores of the stars. And in fact, if you asked a solar physicist, what's the sun made of? They would say 75% hydrogen, 25% helium, and trace elements. Mm-hmm. All of the stars over the life of the universe have only added to the trace elements. The universe is still predominantly hydrogen and helium with the same ratios as it had at the start, which is incredible. I mean, these calculations that were done in the 1940s, of course, at the time, those calculations were really hard, but you can now get little scripts on the internet that does all of the nuclear calculations for you, and you can make predictions of what came out of the Big Bang, right? So that works. So you keep pushing back further and further and further, you get into the realm of particle physics, and of course, you need these really high temperatures because these are the kinds of collisions we're seeing at the Large Hadron Collider, right? And so we know that that was the physics that operated back then in the early universe. So we can build this picture of what the universe was like until we start to get into the realm of ultra high temperatures that we haven't recreated in the Large Hadron Collider. And we know that in those super high temperatures, the laws of physics are different to the laws of physics we have today. The forces that were acting are different, the way they acted, the material they acted on, etc. So we start to run into this, here be dragons. But we're now talking of times which are like 10 to the power of minus 35 seconds after the Big Bang. Okay? After the initial start. And note that we don't know when the initial start really was, but we have a point that we can sort of say that we treat this as t equals 0, but it doesn't mean really that we think
was zero.
That was 0.
Yeah.
But so we can push our physics back all the way to that kind of point, and even a bit further. Some people, depending on how flexible you want to be with your physics, you can get to around 10 to the minus 42 seconds. Okay? So we can build up this picture. So from that epoch onwards, we can say this is the way the universe has evolved. And we basically start, as I said, here be dragons a little bit, and then it's like we understand the physics and etc. And you work your way along. I've spoken to colleagues about this, about when would you say that we really understand what's happening? People would bet about a millionth of a second after the Big Bang, right? Mm-hmm. Which I know it's actually a long way from 10 to the minus 42 seconds, but we're talking about like rock solid, really understand what's going on. About a millionth of a second, right? That we have no doubt from that point to 14 billion years, everything's really hunky-dory. Before then, there's a bit more mystery involved, but the mysteries involved the further back you go. And I said we have that barrier at around that 10 to minus 42 seconds that can't look through, can't see the birth of the universe.
Right. So everything depends on light, how far back we can see light coming from that source, would you say? Or the origin of light itself?
Yeah, so we can talk about the origin of the light in the Big Bang, right? So what we know is that the initial birth of the universe was energetic, right? It just is. There's from the energy in the universe today, you can work out that the Big Bang was energetic. Mm-hmm. That might seem like a really silly thing to say. I mean, but there are people who've envisaged effectively a cold Big Bang, a universe that's born without that kind of energy, right?
So Big Bang, it wasn't a bang, was it? The way it sounds like.
Well, it would have hurt your ears if you were there.
Right.
Okay, so yeah, there's a lot of confusion around the birth of the universe and the phrase the Big Bang, and you have to remember. Do you know the origin of the phrase the Big Bang?
No.
Okay. So Fred Hoyle, who is, I don't have many scientific heroes, but Fred Hoyle is one of them. Yeah. Okay. And he had his ideas about the birth of the universe. And in fact, he had this picture where the universe didn't have a birth. He had what was known as the steady state cosmology. Okay. Now, that's a universe which is expanding, but material is being constantly created to fill that expansion. So over time, the universe doesn't change. It expands, but doesn't change, right? And so he was one of the ones that didn't like this notion of the Big Bang being the birth of the universe. Okay, and so I think it was in 1948. He enjoyed doing media and talking about the universe, and he was given an interview to the BBC, and he wanted to disparagingly refer to this notion of the birth of the universe, and he called it this Big Bang theory. Right? So its name comes from essentially a slap across the face rather than anything else. Right?
Interesting.
So, but the name stuck, right? And there have been lots of talk about should we rename it, because it's not really the picture that you should be taking away. Mm-hmm. The other picture that people have, which is incorrect, is that the universe started at a point. Okay, I won't say incorrect. You have to be very careful by what you mean. Started at a point. Okay, mm-hmm. So let's take our universe today as well as we can understand it. And if you asked a cosmologist today, how big is the universe in terms of space, right? They would say, well, in the simplest model, and we can always complicate things, but in the simplest model, it's infinite, right? So I can head off in that direction or that direction. It would be infinite, okay? So you say, well, how big was it yesterday? Well, it's infinity today. It was infinity yesterday, wasn't it? Mm-hmm. And you can keep playing this game, and you get back to day one, and the universe is still infinite at day one. Okay, and you say, well, what was it yesterday at the birth? And it was infinite in extent. And you sort of go, oh, hang on, no, but every book I've read has said that the universe was born as this little dense point. And we have to be careful about two pictures of the universe. There is the universe, and there is the observable universe.
Right.
Okay? So the observable universe is the bubble around us that we can see. Okay? So that goes out to the cosmic microwave background. That's as far as we can see. So that is like a region which is effectively we're receiving light from, finite volume. Okay? But in the simplest picture, that finite volume is embedded in an infinite amount of space. So when we say, the universe started as a point, we're really saying that the observable universe started as a point, but it was a point inside an infinitely large, infinitely dense universe at the start. And it gets confusing because you can play all kinds of games with infinities. It's easy to lie with infinities, but 1/1000th of a second after the Big Bang, it was infinitely large, right? The universe, the observable universe wasn't, but the universe that it is embedded in was.
How does time play out relevant to an infinitely sized universe where there is a beginning of the observable universe?
Yeah. So time is one of those concepts that's tricky to get your head wrapped around, right? Again, in the simplest picture, right, time would have began at the Big Bang, right? So it would have started everywhere, clocks ticking at exactly the same rate. Now people, as I said, don't think that t equals 0 really was the start of the universe. Maybe if you read Lawrence Krauss's The Universe from Nothing, he will say that, again, in this simplest picture, there's a t equals 0 that's the start, but some people think probably came from somewhere. Hawking would have said that there is no time equals 0 because there's no space equals 0, and it's this convoluted thing at the start. So we have this simple picture that time starts when the universe starts and has just marched onwards at some level from that. The problem that we have with the universe is that when Isaac Newton spoke about time was relatively simple, right? In that effectively there was a universal clock that ticked 1 second per second, and it was synchronous across the universe, right? So everybody's clocks would be in sync, okay? Einstein comes along, and that notion of time goes out the window, right? Time becomes relative. Mm-hmm. So if you and I have clocks and we synchronize our clocks and we go off and do stuff and run around and move close to the speed of light relative to each other, or go into different gravitational fields, etc., and come back together, compare our clocks, different amounts of time have passed. And of course, we can thank Christopher Nolan and Interstellar for demonstrating this to people, even though the emotions in that movie were all over the place. So time becomes very, very convoluted in some sense in our universe, because there is no like regular beat of the drum that the universe is following. Every sort of individual piece of the universe and everything in those pieces of the universe have their own little clocks which are ticking away, and they're not synchronized.
Right.
Okay? It gets very, very messy trying to understand how the universe effectively unfolds from moment to moment if you don't have a synchronous now, or a notion of a synchronous now. But again, this is something that philosophers love. Physicists sort of shrug and try and get on with things. But there are those that think that this notion that time is ticking differently in different parts of the universe might actually influence the way we observe the universe. And so I have a colleague over in New Zealand, David Wiltshire. He's been working on his cosmological model for a number of years, the timescape model, I think it's called, where you have to worry about the relative rates that clocks are ticking in the universe if you're going to properly account for what we see through our telescopes. And from his opinion, that we're being fooled about some aspects of our observations because we're not taking this notion of time properly into account.
One of the things I was reading a few days ago actually was there was a statement there in the article which said we humans are made of stardust. How true is that? And then if we are, another part of that article said about 5% of the universe, approximately 5%, is stardust. Everything else, or is matter, and everything else is dark energy or dark matter. Dark matter and dark
energy. Yes.
Okay.
All right.
What's happening there?
So okay. Let's deal with the first thing. We're made of stardust. Stardust. It's a really romantic thing to say, isn't it? But so are flies and maggots.
Yep.
Right. So okay. So what do we mean by stardust? Well, in truth, you're not made completely of stardust. Okay. So you're mostly water, which is hydrogen and oxygen, and that hydrogen came from the Big Bang. Okay. So then there's the question of all of the other elements. And of course, for us, carbon, oxygen, iron, all of those elements are important. Where are those elements made? The only place you can make elements like that is in the hearts of stars. Our sun shines by converting hydrogen into helium, and our sun's not really massive enough to play this game. Our star is a little star, but more massive stars that can have bigger pressure on their cores so that temperatures are higher, you can then start to burn helium into heavier elements, so into carbon and then oxygen, etc. So those elements get made in the hearts of stars. So, okay, that's good. Big problem is that they're in the hearts of stars and they've got to get out. And so there's no point in having those elements there if you want to use them to form planets. But it turns out that the ends of the lives of stars can be traumatic, right? So our sun, when it gets older, right? So it's created hydrogen, helium. Some of that's going to leak into its atmosphere, etc. Our sun, when it gets older, it's going to become cantankerous, right? So what happens is that the sun uses up all of its hydrogen in the core, so it's got no more fuel, and it sort of has to readjust itself to start burning helium. And that's not a good thing for the sun. And actually what that does is it upsets its internal sort of constituents, and our sun would actually start to swell and grow, and it becomes a red giant star. And so it will become larger than the orbit of Mercury, larger than the orbit of Venus, probably larger than the orbit of the Earth, and that will be the end of the Earth. And eventually the outer layers will be blown off into space, and those layers, the gas will mix with other gas, and it will go into the next generation of stars and planets. But the place where you get a lot of elements released are when massive stars die. So massive stars, 10, 20, 30 times the mass of the sun, their nuclear engines, they burn ferociously, right? So they burn their way through silicon and sulfur and all this kind of stuff. And they burn and burn and burn and burn and burn until the core starts producing iron. So the core becomes more and more iron enriched, right? And there's a problem, is that iron, you can't burn it in a nuclear reactor. You can't take iron and get it to join together and release energy. Okay, iron is the most stable element. So again, you've probably seen this the binding energy per nucleon, and it's sort of stuck at iron. So that means that the core of the star stops burning, right? So it goes out, boom, and that means that the rush of energy from the core outwards stops. And that means that gravity can then start to suck the star inwards. So the star crashes down onto the core, putting energy into the core. So that drives iron into heavier elements, so things like gold, right? Formed when massive stars die. There are other places we can do it, neutron star collisions, but let's worry about massive stars. Crash down on the core, make really heavy elements, plus you've got all that oxygen and carbon, etc. That crashing down the core releases this burst of energy, and then boom, the star blows itself apart. So that's a supernova, right? And you get the vast chunk of all those heavy elements, right, get blown out into the interstellar medium, into the galaxy, mix with the gas that's there, and then that gets caught up in the next generation of stars. So I can say with confidence that the carbon and oxygen and iron in your body was at the heart of a star. And it might have been at the heart of a couple of stars, right? You might have gone through several generations of star, birth, life, and death until the elements ended up here on the Earth. The gold was created in some of the most violent events in the universe, right? Up to uranium, right? So the uranium that you dig up in northern Australia, again, was formed when a massive star died. So yeah, we are stardust, right? So that's definitely the fact. Now, the other thing you mentioned is about us being 5% of the stuff of the universe. And in some sense we are, right? 95% of the stuff in the universe. So 70% is dark energy. What is dark energy? We don't know. But it's driving the expansion of the universe. It's accelerating the expansion. 25% is dark matter. The dominant mass in the universe provides the dominant gravitational fields in the universe. What is it? We don't know. In fact, I'm writing a grant at the moment. Hopefully we'll get some money to try and work out what dark matter is. 5% is atoms, okay? But I've already just lied to you, because it's not 5% is atoms. 5% is the stuff of atoms, okay? Protons and electrons. But most of that stuff is in the form of a plasma. Right? In the sun, there are no neutral atoms. Okay, in interstellar space, intergalactic space, there are no neutral atoms. So you only really get neutral atoms in cold gas clouds and on planets, etc. So the percentage which are stuff like us, right? Planets, etc., is a fraction of a percent of the stuff of the universe.
Fascinating.
Yeah. So honestly, the way you have to look at this is that we are barely the sort of sugar on the icing on the cake kind of thing. We're barely there. And this is one of the things that at some level we have to appreciate, is that the universe would happily get on without us. If the universe didn't have any atomic material, it wouldn't care. It would continue to do its thing. Stars would shine, etc. Yeah. But we are such an irrelevance to the stuff of the universe.
Right. But then would it achieve complexity?
Well, this is the thing. I mean, we are here because of the complexity that you can make. The fact that we have a periodic table at all, we're a reflection of all of that. But yeah, for the universe would have still managed to do stuff, but it wouldn't have ended up with the kind of complexity that you need for life.
That's interesting. So if we in some way crack open the understanding of dark matter and dark energy, do you think it'll rewrite the way we understand universe?
It has the potential, right? So again, the big mysteries about dark matter and dark energy. So let's start with dark matter. Right, we've known dark matter has existed for 100 years. The first sort of measurements where people were saying, "Oh, there's something weird going on," was in the early 1910s. 1936 was the first mention of Dunkelmaterial, it was German for dark matter. By the 1970s and into the 1980s, right, it was known that galaxies weren't behaving the way we expected them to. You needed more mass there to hold them together. Okay, so we know that there's more stuff out there, more gravity out there than we expect, right? What is it? Now, the thing is here on Earth, we've done lots of experiments and we've come up with what's known as the standard model of particle physics, right? So, the Higgs boson was the icing on that cake back in 2012, but we've got leptons and quarks, they're the fermions, we've got bosons, etc. So we can explain everything that comes out of the Large Hadron Collider with these particles that we have. But there's no dark matter particle in there, right? Where is it? It should be in this family of stuff. If this stuff represents the subatomic universe, where is the dark matter particle? And so this has been a big motivation. People have been trying to extend the standard model to sort of find a space for a candidate for what could be all of this extra mass that's out there.
Sorry. So every entity in the universe has why there has to be a particle necessary for dark matter to exist.
Okay, so again, it's not the only possibility. Okay,
right.
So possibility number one is stuff, right? It's material stuff.
So we know that it is material stuff.
No, we don't.
We don't.
It's a possibility that it's material stuff.
Yeah.
And I think it's the possibility that most people sort of would bet on is that it's material stuff. Mm-hmm. So if it's stuff, what is it made of? Well, everything we know of, all the stuff we know of is made of particles. And at some level, you get down to the fundamental particles, right? Mm-hmm. You are made of up quarks, down quarks, and electrons. That's it. No matter all of your complexity, right? Because they're protons, neutrons, and electrons, and that makes up everything to do with you, right? So you would imagine that that dark matter would be made of a fundamental particle, or particles that can get together and do stuff, but not interact with light, so they don't have an electromagnetic signature. And we've got this mathematical structure for predicting the particles in the standard model, right? We start off by discovering that we've got electrons and neutrinos and quarks and then bosons, etc. But then we realized what the mathematical structure was, and we were able to predict, I expect there to be a top quark and a bottom quark and a W boson and a Z boson. We found those. But nowhere in the mathematical structure we currently have does something pop out and say, I'm the dark matter particle. Right? Nothing has the right properties. So you have to assume that, maybe the mathematics is not complete, right? Maybe we need to add bits to these mathematics, but like all mathematics, there are multiple directions, infinite directions that you can expand a set of mathematics. And so we have candidates that people are proposing for potential dark matter particles. I add this bit of maths on or that bit of maths on. For those that know, this is adding terms to the Lagrangian. That's what you're doing for different interactions. And so you get dark matter particle predictions, and you go looking for where those particles would be. The Large Hadron Collider, we haven't seen anything yet. The other side, of course, is that you could say we've got gravity wrong. We've got the mathematical formulation of gravity wrong. So today's mathematical formulation of gravity is Einstein's general theory of relativity. Okay, it works really well, right? It works well in the vicinity of the Earth, right?
On Earth, yeah.
Yeah. So the GPS system works really, really well. The perihelion shift to Mercury, all that stuff works really well. So you need to show that Einstein's theory is wrong, but that wrongness only shows itself at large scale when you get out onto galactic scales.
Right.
And people have proposed mathematical models for this, but some sort of work. The problem is consistency, right? The thing with gravity is that you need to explain a lot of things, right? So you might say, oh, look, I've modified my law of gravity, and then somebody says, well, this predicts that an apple, when it falls from a tree, should crash through the earth, and you sort of go, oh, well, okay, that's not right. So nobody has come up with a mathematical formalism that can really account for gravity as we see it, right? In terms of explaining dark matter and also explaining what we see here on the Earth.
Right.
So those are the sort of possibilities that we have. But there's a lot of effort to try and find a dark matter candidate. There are experiments here in Australia, in Europe, where people are trying to capture dark matter particles. The big problem you have is because they don't interact electromagnetically, means that they don't interact with materials in a way that you'd expect, right? They would tend to go straight through things because they would only interact maybe via the weak force, which is like a very weak interaction.
Talking about gravity, black holes.
What about black holes?
Well, it's a very interesting topic, isn't it? There is a black hole, or a supermassive black hole, at the center of a galaxy. Is that
yes?
So?
It's not supermassive. It's 4 million times the mass of the sun. That's not a big.
That's small.
Well, you can get black holes on the scales of billions of times the mass of the sun. Billions of times, yeah.
Wow. Okay.
So they're big. So the sun has got a big black hole, but it's not up there with the really big black holes.
Wow. So why are they there? Is there a role they play in the center of a galaxy, or is part of the formation of a galaxy and the black hole sort of a relative story?
Yes, I think most people would say it's the latter, right? So you mentioned there's a black hole in the middle of the Milky Way, but when we look at galaxies, we tend to find black holes in their middles, right? So we look at Andromeda, we see that there's black hole there. And we look out into the universe, especially into these super hyper bright galaxies called quasars. They're the ones with these really big black holes. So what it's thought is that the formation of a galaxy is probably a rather violent event. And what I mean by that is that there's probably a lot of big stars formed very quickly that live very fast and die very young, producing black holes in a small volume. Those black holes crash together to form bigger black holes, etc. And so it's thought that there is like a relationship between the growth of a black hole in a galaxy and the growth of the galaxy itself. And there's a relationship called the Magorian relationship between how big a galaxy is and how big its black hole is, which sort of suggests that they are related in the way that they grow. Right? So, but that's tied to the fact that, that probably the initial stages where there's a lot of stuff going on, which sets the scale for what a galaxy is going to be, had these rather dynamical and vigorous events going on that allowed black holes to grow very quickly.
The light and time, which you discussed at the beginning of the universe, as in case of a black hole, how do they so I understand that there is something called as an event horizon of a black hole.
Yes.
What is it, and what happens as you are at the event horizon to light and time? Okay,
so the event horizon is not a thing, it's a boundary.
Right.
Okay, and the best way to think of it is as a one-way membrane. You can cross in, but you can't cross back out.
Right. And that's because of the gravity?
Yes.
Yeah, right.
Yeah. All right. So let's imagine that I'm going to drop you into a black hole. Okay?
No.
So firstly, off you go and you start falling. So you drop towards the event horizon. Okay? And imagine you've got a a watch on, you're looking at the time as you're falling down, etc., what would happen? So as you fall, you're watching your watch, it's ticking away at 1 second per second. And you sail straight through the event horizon, and you end up actually crashing down into the center of the black hole. It's a bit messy, so we won't talk about that. So to you just fall in, nothing happens to your clock, everything's fine. But what about me, who's watching you falling, right? So off you go, and you start falling in, and everything's fine. You're probably screaming a bit, but we can live with that. But as you start to approach the event horizon, something bizarre starts to happen to my view of you, okay? So as I watch you, okay, say I could see your watch on your wrist, I actually see your clock start to slow. So instead of 1 second per second, I'm seeing 2 seconds per second. No, that's getting faster, right? Half a second per second. I see your watch slowing down, okay? And as you get closer and closer to the event horizon, it gets slower and slower and slower, until when you reach the event horizon, the clock stops. But I don't really see you anymore, because what actually happens as well is that I see that the light coming from you starts to get stretched, right? So the wavelength gets longer and longer. So if you imagine that you're wearing a white t-shirt, say, I actually see that t-shirt start to turn red. Okay, so the wavelength of the light is getting longer.
Right.
And your screams get drawn out longer and longer and longer. In fact, the stretching gets so long that as you approach the event horizon, the wavelength of your light stretches into microwave and then radio, and then you vanish. Okay? So, what we've got, these two different viewpoints, right? You fell in and everything was fine until you got down to the center. But at the event horizon, I never saw you cross. And what's actually happening is that it's taking light, it's harder and harder for light to get away from the event horizon to get to me looking at you. So as you initially fall in, light is happily just traveling. But as it gets closer and closer, it takes harder and harder for the light to sort of escape until you hit the event horizon, and light at that point can no longer head outwards from the black hole. I can never see you cross the event horizon. Okay? So once you're inside the event horizon, that light that you emitted can't get through the event horizon. It basically folds back around and follows you down to the center.
How do we know all that? How do we know that light?
From the mathematics.
Right.
So, I can only tell you what happens with a black hole from mathematics. We haven't got one in a laboratory to do a test on, right? So from the mathematics, and the mathematics has been around for over 100 years. So the initial solution was provided by Schwarzschild back in 1916. And even though black holes weren't discovered astronomically until 1960s and into the 1970s, they were a theoretical curiosity, and people worked with the theories, right? What is kind of interesting is that Einstein, who knew about this issue, that you can't see anybody fall in, he concluded that you could never form black holes, right? Because if stuff never crosses in, how could you form a black hole if stuff never gets inside the event horizon? So it wasn't until after Einstein's death, so he died in 1955, I think, or 54, 55, that there was a paper published by Finkelstein who pointed out that yes, that's the viewpoint that you get, but this notion that things can't cross in is incorrect. Things will happily cross the horizon in their own viewpoint, but you won't see them cross from outside. So you still get this notion that black holes will form, matter will fall into the black hole, right? But you get this really weird view of stuff never crossing in from the outside.
Right.
And there are people that have hypothesized that that there's almost like an imprint of everything that fell into the black hole stuck on the event horizon, or the last bit of light that was emitted that can't escape is stuck there coming outwards. It turns out things are a bit more complicated than that, but yeah, event horizons are weird things.
So when I fall into the black hole, what's on the other side? Where do I go?
All right.
Where am I going?
Okay. Here we go. This is going to be interesting. So number one, let's just take the simplest of black holes, which is the Schwarzschild black hole. So it has mass, and that's its only property. Okay. All that mass is crushed down to a point, right? Singularity, which probably is not really a point. We have to work out why our mathematics say that it's infinitely dense, and you would fall towards that, and whatever else is around you would also be in falling. Okay, so inside the event horizon, everything has to fall. Even if you had a rocket pack on, the most powerful rocket ever, and you fired it as hard as you could, you still fall. Gravity wins within the event horizon. Okay?
Wow.
Gravity wins is also bad news for you, because what actually happens is that because the gravity is strong, and then you get to a point where the gravity is changing quickly. Okay? And what that means is that the gravitational pull on your feet is stronger than the gravitational pull on your head. Right? So your feet want to accelerate more than your head does. That's not good for your body. Okay? So essentially, it would be like you were on the rack. In medieval torture, you would be stretched. So this is known as spaghettification, right? Because you turn into this long, thin bit of spaghetti before being pulled apart. So who wants to go through that? That's not fun at all. So you need a get out of jail free card, and the way you can do that is you can jump into a rotating black hole. Okay, so we mentioned the Schwarzschild black hole has just got mass. A rotating black hole has got mass and angular momentum. It's got spin, right? So rotating black hole. Okay, so does that sound any different? Well, once you're inside the event horizon, you still have to fall. Okay, but when you get very close to the center, things calm down a bit. It's a bit like, the eye of a hurricane. Things calm down. You don't have to fall anymore. And it turns out that in the center, that point mass, because of rotation, has been drawn out into basically a hoop. It's a ring. And there has been a lot of speculation about what that ring actually means. So Roger Penrose, who got the Nobel Prize in Physics only a few years ago now, he actually thinks that ring inside the black hole is connected to a different gravitational structure, which is known as a white hole, potentially in another universe.
Okay.
Right?
I'm going to another universe.
So you jump through the event horizon, you go through this ring singularity, you pop out the other side in something known as a white hole, you find yourself in another universe. And again, this sounds really bizarre, but have you ever seen the 1970s Disney movie, The Black Hole?
The black hole, yeah.
Right, think about what happens there. They fall into the black hole. They appear to go through hell, but they then pop out in another universe, right?
Right.
So
it also reminds me these Marvel movies. Thor comes out of it's like a wormhole sort of thing.
Yeah. Well, I must admit, I stopped watching superhero movies after like The Incredible Hulk in the 70s. I never, Marvel didn't work for me.
Really? Wow, they're fun.
This is a complete aside. I saw Batman in, what was it, 89? Was that that's when Batman came back. That was great. Then I unfortunately watched the George Clooney Batman a few years later, and it's like, that was it. I'm done. Superheroes are not for me. But yes, I understand they've been relying on multiverses and wormholes and things.
To get from one place to the other.
Yes. Of course, but the real question is, so Penrose says that's what he thinks the maths tells him. Who's going to be the brave person that jumps in? Because you can't send a message back saying, it's actually okay in here, right? And so you might think, what if I jump in and I'll take a camera lead with me, right? But
a mobile probably.
but you fall and electromagnetic signals fall.
I see.
Right?
Yeah.
So you're not going to get a message out to the outside world. So you'd have to be a brave person to jump into a rotating black hole to see if you come out on the other side.
Right. All these years of cosmological research, if there was, imagine if tomorrow there was a voice out of the sky which said, Geraint, ask any one question, right? And I'll give you the answer. What would that one question be?
The first question would be, why does tax law make so little sense? Because I've been.
Ask that.
No. So, but this is the kind of thing, right? I mean, so look, I am a human. I have a job. I have to pay taxes. I have to pay mortgages, etc.
Right.
And I just don't understand why some of it is set up the way it is. I'm sure it's just the madness of men and women, or whatever you want to say. Anyway, but let's go big questions. Don't worry about.
That's why they have lawyers.
Well, exactly. I think it's just a big scheme for people to make sure they keep getting paid, right?
Right.
Anyway. No, so I guess if it was a big question, can I ask more than one? Is it like a genie?
Okay, 1.5.
Okay. Oh no. So I'd try and cage it so I can get the biggest answer possible. So, is this all there is, right? And what I mean by that is, what is this universe in terms of its relationship to other universes? Is there more? Is the multiverse a thing? Is it bigger? Is there other stuff out there? Is there other universes where there are other beings? Are there beings in our universe? All this kind of stuff. Is that, what is the big picture of our universe in relation to whatever else is going on out there? So it's not a very specific question, but I feel like if I could ask a specific question about our universe, what is dark matter, right?
Right.
That feels like the tax question,
Right.
at some level, right?
Yeah.
So I would want to ask something big.
Right.
Yeah.
Yeah. No, that's what is that question, right?
Yeah.
You would ask, and it reminds me of Douglas Adams.
Oh yes.
Right.
Yes.
What is the right question to the answer that is the universe?
Yes.
Right?
Exactly.
Are we thinking about the right question of the to ask? Right.
Yeah.
Geraint, it was a pleasure talking to you. Thank you for your time and wonderful insights into the mysterious world of the universe, black holes, stars, and galaxies. It was great having you.
Thank you very much, and I'd be happy to chat again in the future.
Thank you so much. Thank you.